In our next section here, we're going to go through redistribution case number 2, which is very similar at first glance from redistribution case 1, but we're going to see that there is a key change and a key functional difference between these two. So if we look at the topology, again, very similar to the previous one where we are redistributing EIHRP into OSPF on router 1. We're redistributing OSPF back into EIHRP on router 3. And then on router 9, we're doing redistribute connected. Where specifically in this case, if we look at the configurations, again, there's nothing very strange going on here. We're on router 1, we're simply saying redistribute EIHRP 100 subnets. Router 3 is redistributing OSPF 1 in, and then router 9 is doing redistribute connected. Now, as we talked about in the previous case, there is going to be an issue that we know of here, that the metric is going to be seated incorrectly on router 9, where the delay of the connected link is going to be higher than the delay of what router 3 is advertising. But let's say that we take that out of the case. So let's change the metric values when we're doing redistribution so that on router 3 we're advertising a worse delay value than the original advertisement. So let's look at what, or in other words, let's set them to be equal between the two of them. That would probably be the easiest, where we redistribute on router 9 into EIHRP, and we're going to set the metrics to be equal. So on router 9, let's say show run section EIHRP, and then under EIHRP 100, we're going to say redistribute connected, and we're going to set the metric to the same value that router 3 is advertising. Okay, next let's go ahead and do our connectivity test. So we have our TCL shell, our TCL script, that is just pinging the different loopbacks of the routers. And first we're going to look at this without a high repeat count, just a basic connectivity test to see do we have reachability between all of them. So let's do this on all the routers at once. I'm simply going to paste the script into all of them. And it looks like we do have connectivity to everything. But notice here what's different between the routers. Some of them appear to have partial reachability to the loopback of 9, where router 1, it lost 1 out of 5 packets, router 2 lost 1 out of 5. Some of the other devices, though, have full reachability, like router 7 was not able to, or was able to reach it without any problems. Router 8 lost 2 packets, router 9 was 100% successful, that's directly connected. But this is one of the type of issues that's much more difficult to trace down, because if you had this in a real design, the user says, you know, the website is slow or whatever the performance issue is, if you have 98% packet success and 2% loss, there could be so many variables that come into play, it's very hard to track down. So let's look at this now. Let's assume that we did the pings, and when the ping was running, it happened to be at the exact point when the control plane was not having an issue and that it was correctly converged. So if we just quit the shell, let's go ahead and just do a ping to 151.99. And from there, from router 10, we can see it's 100% successful. But now a few seconds later, we try it again, and there's some sort of loss. This is where we need to think about what are the other tools that we have in the network besides just doing a reachability test, because that may not actually tell us what are all of the other variables that are actually going on. Okay, the other two that we're going to look at in this particular section is how the IP route profile feature works, and then how to read the debug IP routing. So the first thing we're going to do is on all of these boxes, we're going to go to global config, and we're going to simply say IP route profile. Now, the IP route profile is an old feature that never really was used that much. There was not a very large application for it because there's other better ways to do what it's trying to do, which is basically to take statistics on the routing table. Because in a real design, you would probably just poll the router with SNMP and ask it, what is your routing table? And then you poll it 30 seconds later and you see if there's any change. Or you could do debug and then send the traps remotely to say this was the particular change that happened in the routing table. But what the IP route profile feature does is take a periodic snapshot of the routing table and it collects statistics on what is changing over time. So it's simply one command globally, which is just IP route profile, and then we're going to look at the show IP route profile. Now, what's kind of bad about this feature is that it doesn't tell you specifically what is wrong or what has changed. It just tells you that something has changed. That the way that we read this specifically, and their description here is a little bit confusing, and at least in my opinion, it says, IP routing table change statistics, the frequency of changes in a 5-second sampling interval, how many changes happened during that interval, and then how many times during sampling did that actually occur. So basically the way that you read this table is that if only the first row is incrementing, it means that there were 0 changes over the interval where the interval is 5 seconds. Now, if we saw that there were 5 changes per interval, and this forwarding path incremented to 1, it meant that in some sampling interval, and we don't know exactly which one, but it meant that there were 5 changes that happened between 0 and then the next 5-second sample, but we don't know exactly what they were, just that there was a change. Now, specifically, the way that we use this feature is not to look at it here on router 10 because nothing is actually changing on 10. We would need to look at it basically in all of the routers in the topology and see, are there any devices that see periodic changes in the forwarding paths. So if we were to go to router 1, this is an indication here that it says something is changing, that 27 times there were 2 changes per interval where that interval was 5 seconds long. There were other intervals where there was 1 change where there were 14 prefixes that were added. But again, it doesn't tell us what exactly it is. The only thing that this is sampling is what is the stability of the table. So if the table is stable and nothing is changing, nothing is churning, we should only see the first row incrementing. Now, once we've found the box that the changes are actually occurring on, there's a couple different things that we can do. So let's go through the other ones and look at here. Is anyone else's routing table changing? Router 2 is fine. Router 3 sees changes. Router 4 is fine. And let's mark these off on the diagram here specifically. Okay, I'm going to circle here which ones are actually having problems. So we saw router 1 is having problems. Router 2 is not. Okay, 2 is fine. 3 is having problems. Router 4 is fine. Router 5 has a couple changes, but we'll say maybe 5 there's an issue, not 100% sure. Router 6, there's definitely some problems here. Okay, as the numbers start to increment down here, this is really when it's saying there's a lot of changes. Okay, so router 6 is also suspect. Router 7, there's changes there. Router 8, it's not. And then probably router 10 is not as well. So this is pretty much an indication that there's a problem somewhere in the eIGRP network, and it's not an issue on router 9 either. But again, this doesn't tell us what the problem is. So next thing we need to look at is, in the debug, which routes are actually changing. Which ones are getting removed, which ones are getting added, and why? Is it a change of the metric or is it a change of the distance? Because again, the difference between the two means that there are different tools we can use in order to solve the problem. There might be certain cases where using route tagging will not help. And it depends on, again, what is the root cause of the issue. So the next thing we're going to do is on all of the routers, we're going to debug IP routing. Now, this is one of those debugs that if there is a lot of churn in the routing table, you probably would not want to send it directly to the console. In my case, I'm going to show it live here on the console, but in a real design, what you would want to do is say something like logging console at level 6 or anything below 7, and then probably log to the buffer at level 7. And then you can simply show log and then see were there any actual changes. Okay, but in this case, I'm just going to log directly to the console. Okay, we can see on router 9 here, it says that some things are changing. I was adding some new routes, and they're being updated via eIGRP. Okay, that was in the log buffer. So let's look at some of the other routers. Who did we see had a lot of changes on? Let's say like router 1, for example. On router 1, and I need to go to global config first, or exec mode actually, and debug IP routing. And we should see every 5 seconds that it's collecting these statistics. And let me make sure I'm logging to the console. Logging, console 7, logging is on. Okay, there we can see the route flap on router 1. So we're adding an update, and then it says we're deleting it. Now, here on router 1, it doesn't necessarily tell us what the problem is, just that we know that the table is not currently stable in its current state. So the prefix was getting added, the prefix was getting removed, but it doesn't tell us the reason. What this means is that the problem is not on router 1. Because if it were to tell us the specific reason it was flushed, then we would know who exactly is making the change. So from router 1's perspective, let's look at specifically what it is saying. It's saying, first off, that I'm updating the routing table, that I had to delete a route to 151.99, and I was deleting it via router 3. The distance was 170, the metric was 3584, and the protocol was EIGRP. Okay, then we start to get an update. An update came in from router 6, where specifically it says here that the metric was 3584, the distance was 170, but now we have to delete it. We're adding it through router 3, we can see that the metric is now closer between them. So if we were to think about this from the view of the topology, why would router 1 be receiving the update from both of them? And this is actually the key change in this case versus the previous one, that now router 1 and router 3 are running both EIGRP and OSPF on their connected link between them. So let's think about now what is the process of the advertisement. So starting at router 9 is doing redistribution into EIGRP. So this goes in as an external EIGRP route, but the metric value here that we used on router 3, it was the same as what we did on router 9. So that might not necessarily be what the problem is yet. So the route goes up to 7. 7 is going to install it via router 9, and 7 passes it to 6 and to 3. Okay, as of now, there's no other redistribution. So now the network, while it's converging, right now it's stable. Router 3 has the route through 7. Router 6 has the route through 7. Next, the route goes from 6 to 1, and 1 is doing redistribution. It's taking the route from EIGRP and it's passing it into OSPF. Once it gets here, router 1 is flooding it 2 different ways. It's flooding it on the directly connected link to 3, and it's flooding it on the route to 5, the link to 5. 5 then takes it and floods it to 4, and floods it back to 1 and to 3 over the DMVPN. Router 1 is automatically going to remove that advertisement. It knows that it was the originator of the LSA, so even though OSPF is not using split horizon, it doesn't matter. That's part of the normal flooding rules. So if you were to debug IP OSPF flood events, it might look a little bit confusing that one is originating the update but then getting it back. That's actually the normal case. That's why you typically want to use the designated router on LAN segments when you have 3 or more boxes, because you don't want to constantly flood all of the LSAs everywhere. Now, eventually the case will work itself out, but it's inefficient for the control plane to do that. So it is normal, though, in some cases like this, to flood the LSA back to the originator. Okay, now it gets to router 3. Router 3 floods it up to 1. Through OSPF, 1 discards this again because it says, I'm the originator, I'm not going to use it. But now here's the key change. Router 3 is now installing the update via OSPF via router 1. Because if we look at what is the difference between 3's route that direction versus 3's route this direction, it's the number of hops. Now, assuming everything is equal and that the OSPF metric is simply a hop count, it really would depend on what's the underlying bandwidth of the physical links. But without changing anything, normally the tunnel interface is going to have a low bandwidth artificially, which means it should have a higher OSPF metric. So this means router 3 is going to prefer to route to 1 versus routing to 5. Now, however, once it receives that update in, there's nothing telling 3 that I cannot originate this to EIGRP and send it back to 1. Because from router 1's point of view, this is not an OSPF route, it's an EIGRP route. That's the reason that it's doing the origination to begin with, that it's being redistributed from EIGRP into OSPF. Now, in the case that router 3 advertises the route to 1, and if 1 sees a lower metric via 3, it means the redistributed route has to be flushed, the new route has to be installed, a new route has to be redistributed, and the process churns. Where we would specifically see this problem is on 3. On router 3, we should see it arguing that there is a closer administrative distance through OSPF. 3 is now the source of the route flap. So on the other devices, when you're looking at the debug, you can tell that there is a problem in the table, but the goal of the debug is to try to trace it back to the source. Who is the one that's actually flapping the route? And in this case, it's 3. So 3 is saying, I originally got the route in from EdgeRP. So I got it in from EdgeRP, and it came from router 7. So now I'm going to advertise this into the rest of the EdgeRP network. Okay, then router 1 does redistribution, and it comes back in, and it now has a closer administrative distance. So now I have to flush out the EdgeRP route. I have to install the OSPF route. This now means that I start to perform OSPF to EdgeRP redistribution and advertise this to router 1. Router 1 now says the route that came from 6 is no longer valid because 3 is closer. But remember, on router 9, we seeded the metric the same. So what would be the issue here? Why would 3, or actually 1 in this case, why would 1 say that 3 is closer versus 6 being closer? If we look back at the topology, why would 1 even make this decision to begin with? Well, what's going to be the deciding factor from EdgeRP? If the minimum bandwidth is the same on both of the routes, the metric becomes a hop count because we're incrementing the delay on a hop-by-hop basis. And if all these links are all gig everywhere, they have the same delay, and from 1's perspective, it says that 6 is further hops away from 9 than 3 is. So 3's route gets preferred, the old route gets flushed, and then the table starts to loop. What's interesting about this, though, is that if we do the TCL test, we might not see it in all cases, though. So let's say we're going to send 10,000 packets, and we're going to ping just router 9. So we didn't even, well, let's say 1,000. 10,000 will take too long. So on all the routers, let's undebug all, and then let's do the ping. So everything looks pretty good up to this point until 9. But look at how many packets were dropped. Really not that many. So if we had been testing the control plane at any point here, we would have thought everything was fine. It's only once we either look at the routing table statistics with the IP route profile, if we were to debug IP routing and actually see the changes, or if we were to look at show IP route and look at the age of the routes. So for example, on router 7, if we show IP route 150.199, it says how long ago was the update received in? 1 second. But EdgeRP doesn't do periodic updates, right? It does do periodic hellos, but it normally should only send an update when there's a change in the topology. So we can see this on router 7. We can track it by doing this over and over and over, but the issue is that you would have to know what routes to look at even to begin with. So this is why, again, you have to try to predict these potential problems in the topology before you even get to the issue. That if you didn't know that router 1 is learning it in multiple ways, and it has to make a decision on one versus the other, which one that gets installed in the routing table dictates how it does the redistribution. Then we can end up in basically this infinite looping process of the control plane that the route gets advertised this way, gets redistributed, comes back in, gets flushed again, gets redistributed, and over and over and over. So in other words, the topology is never going to be stable here. We could leave the IP route profile on, come back an hour later, and we would see tons and tons of changes. So that would be a good indication that there is a problem, that the control plane is not stable, and then we would need to look at the debug to figure out specifically why. Now, of course, you could just do the reachability test to all of the destinations and then collect larger statistics over time, and that would tell you which of the destinations are actually causing the problem. So, for example, if we went to all of the routers and said we're going to ping router 9 and we're going to ping it 100,000 times, then when you look at the packet loss, that should be obvious that there's a problem. But the issue here is that that assumes that you know there is a potential problem and you know which routes to look at. So what I would personally recommend to do is that once all the redistribution is done and everything is stable, then turn on debug IP routing. Don't clear the routing table at that point, just clear out the logs to make sure that there's nothing in there. Come back about a half an hour later or a couple minutes later and see if anything has changed. If it's not something that is supposed to be changing, like you didn't clear the routing table or you didn't add new redistribution or didn't add new prefixes, then it means there's something unstable about the control plane. Other than that, the protocol should not be sending periodic updates. RIP, of course, will. So RIP, based on whatever the update interval, is going to keep refreshing it. OSPF would refresh, but only every half an hour once we get to half of the max age. OSPF, you can prevent this like we talked about if you set the do not age, the DNA flag, by doing something like IP-OSPF flood reduction or setting it as a demand circuit or other things like virtual links and sham links set DNA, but EIGRP should not be sending periodic updates. It's only when the route goes active, when I send a query and then I get a reply, should EIGRP be doing any convergence. Okay, so now we figured out, or narrowed it down a little bit further, where is the problem, but we don't yet know how to solve the problem. Okay, what is specifically the problem in this case? We know that router 3 is flapping the route, but why is it flapping the route? Okay, let's trace the path of the route again. It's coming from 9 to 7, 7 sends it to 3. Currently, 3 is not doing redistribution of EIGRP into OSPF, which actually will change this case. And it would change the previous case as well. Because if you are the originator of the LSA, you will not listen to other originations. So there is actually one very simple solution that I didn't talk about in the previous case, is do mutual redistribution both ways. Because if I am originating the route from EIGRP to OSPF, I set myself as the LSA5 originator. When someone else's advertisement comes in, I say, no, I'm already originating it. I can't listen to your origination. That would be a loop condition. So that's actually one real simple solution to both of these. Okay, someone else had mentioned here, remove the OSPF adjacency between 1 and 3. That could be a potential case. So let's try that. Okay, let's go to router 3, and on the interface, let's say on all these, TCL quit, and also on router 10, let's do this. Let's do the ping, and let's set whatever the maximum repeat count is. And we'll see, are we still dropping packets once we get to our final solution. Okay, so let's let this run, and we can see we are periodically dropping packets. So next time router 3, let's go to the link, gig 1, 13, and say no IP OSPF 1, area 0. So the adjacency now goes down, and let's see if there's a change here. On 10. Well, there is a change. The change is now worse. Change is now there's no reachability at all. So removing the peering between them, that's not the solution. That doesn't fix the problem. Okay, that's not really the root cause. So let's put that back. Let's think about why did router 3 flap between the routes to begin with. So it's saying the route came in from EIGRP, and the AD was 170. It then came back in to OSPF, and OSPF was 110. So again, think about in what case is router 3 allowed to do redistribution. The case is dependent upon, do I have the route in the RIB or not? So is it actually an OSPF route when I show IP route, or is it an EIGRP route? So in this particular case, it's different than the previous one. It doesn't have anything to do with the metric, because we seeded the metric the same and that didn't fix the problem. The problem is now related to the distance. That since the external EIGRP is always less preferred than the internal OSPF, We choose OSPF, that causes us to do the redistribution, and then we're feeding the route back to the process. So the real issue here is that router 3 should not be installing the route as OSPF. It should be routing into the EHRP domain to get there, which means that it won't be able to re-originate it back into OSPF. Now again, there's a number of different ways to solve this. We could filter the route out. We could change the administrative distance. But in this particular case, what's interesting is that setting a route tag will not help us. Because the issue is not that router 3 is redistributing it back into EHRP. The issue is that router 1 is advertising it both ways. So 1 sends it to 3 via OSPF and it goes through another path. 3 is installing that, and that's the one that's getting redistributed in. So we could set the route tag, but it's not going to solve this type of case in every single situation. Now it may actually, now that I think about it, it may solve this particular case, but it won't solve every particular case that's related to distance. And that's why it's important to understand that they are two separate unrelated problems. That some loops that are related to the metric cannot be solved by changing the distance. And likewise, some loops that are related to the distance cannot be solved by changing the metric. So route tags would generally help you in ones that are related to the metric, but not necessarily the distance. Okay, so let's try this. Let's go to router 3 and let's set the administrative distance to external EHRP to be lower than OSPF. So under the EHRP process, we're going to say the distance for EHRP, for internal, we'll leave that as 90. For external, let's set this to 109, so 1 less than OSPF. Okay, next let's look at how the route is installed. If we show IP route 150.199, it says now we're installing it as EHRP, the distance is 109. Okay, let's see if this fixed it on router 10. Looks good so far. So let's go ahead and test the rest of the reachability. So let's say from everyone now, let's do a ping to all the loopbacks and let's let it run for 1,000. So it looks pretty good so far. We're waiting basically to get to 9. And the reason that I wanted to rerun it from scratch, again, is that when we are changing these attributes, we're changing them for more than one route. Now you can change it per route. When you look at the distance syntax, you can say who is the route source and then what is the actual route. Now I'm not 100% sure if you can change this for external EHRP. In older versions of code you could not, but I haven't tested it recently in this newer release. The issue is that when you want to set it, and it's kind of an odd syntax, you would do it something like this, where you would say router OSPF1, set the distance to whatever, 111, from the source of the route, which is an address matched against a wildcard, and then what is the actual route. So you would call a standard access list here that's matching the prefix. What's bad about this implementation, though, is that you would normally want to match a prefix on a prefix list, not on an access list, because we can't match on the length. Now, we'll come back to this and talk about this in more detail when we talk about filtering and look at what are the different ways that we could do filtering in OSPF versus EHRP and other protocols. This is one of the applications where you could set the distance to 255. You could say set it to 255 from router 1 for the route about router 3. And then it would change the distance, basically poison the route. So this is one of the other options. But again, the issue with doing this is that when you match it on a per route basis, if something changes later, you have to come back and reaccount for it. That's why in our previous case, it was easier to use tagging than it was to match the individual routes. Because if a new route is introduced later, I would have to go back and update the prefix list or update the ACL. In the case of tagging, it's saying when you redistribute anything, it gets the tag and then it's automatically prevented on the return path. That's basically what I'm doing here on router 3 by just setting the distance globally for the process as opposed to per prefix. So we're saying that all internal EHRP stays 90, but if I'm trying to make a decision of external EHRP versus OSPF, prefer external EHRP, which means that I route my packets in this direction, which means that the OSPF route cannot be installed in the rib and that I cannot do the redistribution. But again, there's another simpler solution for this, is just redistribute both ways on both routers, because then in the case of OSPF, they're both originators of the LSAs. Now, we'll look at some other cases later where when you do mutual redistribution in both directions, you can end up in some odd cases that are based on the order that the routing process loads. That router 1 might choose to route to 5 to get to 9, depending on if 3's process loads before 1's does, or vice versa. So you end up in some cases where you might not have the end result that you wanted, and it's something that you can't predict. So it's not a deterministic output, basically. Now, we'll also see this in cases with BGP, and there's actually a specific term for this in BGP that's kind of weird. It is called a BGP wedgie, and I swear I'm not making this up. A BGP wedgie is when BGP converges in a non-deterministic manner, these stable but unintended states are termed BGP wedgies. So the IGP process can basically get into the same case where you wanted to go this way, but it converged first in this direction. Then based on what route gets installed in the routing table, it controls whether or not you can do redistribution. And then you route to A versus B, and that's not what you wanted. So, and again, it always depends on the topology, which makes the problem more difficult because you cannot put general cases on these. The only way to realistically solve this is you have to look at the topology visually and trace the route on a hop-by-hop basis. Once you get to the router that is making the decision, you figure out, okay, I'm learning it through OSPF, I'm learning it through EHRP and RIP. Which type of route is it going to be between them? Is it internal EHRP versus RIP? Okay, I'm going to go that way. Is it external EHRP versus OSPF? I'm going to go to OSPF. Which again does make it important that you understand what are the differences in the AD values, that you need to know offhand what internal EHRP is versus external, and then the others. So there's only really a handful that we really care about, which is mainly going to be static routing overrides everything, because it's 1. Then EHRP is next at 90, OSPF is next at 110, RIP is at 120, then we have external EHRP at 170. If BGP is involved, eBGP is always first at 20, and iBGP is always last at 200. So we'll look at some cases later with redistribution involving BGP as well. But again, what's interesting about this particular case is that if you had verified it at the exact same moment that the control plane was allegedly stable, you wouldn't have seen the problem. So that's why it's important to understand how the IP route profile works and how the debug IP routing works, and then to trace it back to who is the one who actually did the route flap, and then you could figure out why are you choosing one protocol versus another, and then make the appropriate change. So somebody had an interesting comment here. It could be dangerous with backup links, that if your main link fails and your backup turns on, when the main link comes back, you may not be able to reconverge that way. And that's exactly what a wedgie means. That in this particular case, it means that you thought you were supposed to reconverge this way, but somehow the table got stuck or wedged in there, and then it wasn't able to flap back to or fall back to the original path that you wanted. But with BGP, we'll see it's an even more difficult case, because when you look at it at internet scale, there's all sorts of other people's decision who influences how traffic is routed to you. So if I'm trying to do like AS path prepending, I'm not really the one who decides how other people routes. I can try to influence it, but I can't guarantee it. So I'm thinking that maybe from router 3, I'm prepending out this direction, but it's too late. This guy is already wedged that way, and it never even learns this route to begin with. Or actually, it would be the other way around, that maybe if they are wedged this way, and the route never even comes in the alternate direction, then even if I prepend out whatever the maximum value of AS path is, the traffic still might come in that direction. So again, we'll come back to those cases later when we talk about BGP specifically. But the key for a lot of this is that you always have to look at the network visually from a high-level overview. If the network is not documented, you would never be able to figure this out, because you have to figure out who is actually routing adjacent with who, where are the potential updates coming in from. If it is the same protocol, you have the same longest match, then you look at the metric. If it's different protocols, same longest match, then you look at the distance. So again, in this case, even though we seeded the metrically correct on router 9, it doesn't solve the problem. Even if we were to do a route tag in this case, it's not necessarily going to solve the problem, because the issue is that the route gets fed back this way, and then one withdraws its own internal advertisement. Okay, there's a question, how did I reduce the problem to router 3 since the other ones were also flapping? The key is that when I looked at the debug on the other routers, it showed me that, and I don't know if I can scroll back to it. Let me start the, well, here, we can see it here. It shows you that there is a change, but it doesn't tell you why. So it says that there was an update that came in, or there was a withdraw message that came in. But I wasn't the one that originated the update. I wasn't the one who originated the withdraw. I'm just listening to somebody else saying the route is gone, the route is added, the route is gone, the route is added. Then you need to trace it back to the person who actually does the original origination, and we traced it back to router 3, and we saw that in this output it says that, and let me undo the distance change. Let's say do debug IP routing. We're going to revert the distance back to the default values. Then router 3 should get an error here saying that there is a closer administrative distance for the route when it comes in from OSPF. And so this is the key field here. The route gets flushed and then it's going to get added back again later. There's a question, how do you clear the counters to 0 on the IP route profile? I don't think you can. I think you just have to turn it off and then turn it back on. So if you go to global config and say no IP route profile, that flushes it out. And then just say IP route profile again to turn it back on. So again, since we still have it running now, if we look at router 3 and show IP route profile, we'll see there's tons of flaps. So anytime you see any numbers basically down here, that's bad. Okay, the only realistic case that you should see this in a real design is with BGP on the edge or BGP in the core. Because converging to BGP table, that's usually not a function of you, it's a function of everyone else in the internet. So if they're not like penalized with route flap dampening or anything like that, if a flap in another portion of the internet will affect you. But that's just normal case that the BGP table is always constantly churning. But in the case of your internal IGP, you should see that the route age is as long as possible. So in OSPF, it should be approaching 30 minutes because that's going to be the refresh timer. In the case of EHRP, it could be potentially weeks if if nothing is actually changing. There's a question here, if I change the administrative distance on EHRP and OSPF to 110, and if we have the same route from both, which prefix would be preferred? It falls back to the default behavior. So whichever protocol had the lower distance to begin with, that's how it behaves. Because again, the routing process internally, they basically accounted for all of these cases, that there must be a tiebreaker in order to choose what actually gets fed to the CEF table. So even though the distance is the same between two protocols, it behaves as if the distance was not the same. So it falls back to by default, whichever one actually has the lower value.